So one last example of our binomial distribution. So this is one where we're actually going to show the relationship of binomial to a discrete distribution. So we have an FFPI survey. It shows that about 80% of all property crimes go unsolved. Suppose that in your town, 3 such crimes are committed, and they are deemed independent of one another. Let's assume that they do meet the criteria for a binomial experiment. And we can go through that, but you can verify it certainly. So we're going to do this a little bit differently than the first 2 examples. So we're going to construct a probability distribution, right? We're going to find the expected value, and we're going to find the standard deviation using the discrete distribution formulas. Then we're going to find the mean and the standard deviation using the binomial formulas, and then we're going to comment. All right, so let's start by constructing our discrete distribution, the probability distribution for this. And the first 2 columns are going to be really easy. The last column is not going to be too easy. So remember, we have outcomes, we have values, and then we have probability. All right, so you remember that from section 10. And there's 4 possible outcomes, right? So the 4 possible outcomes is that, well, we can go ahead and solve 0 crimes. And then we could have 1 solved crime. We could have 2 solved crimes. And we could have all 3 of the crimes solved, right? And the values would be 0, 1, 2, and 3. Right, now, the probability, all right, so let's make sure we understand this. All right, 80% of all property crimes go unsolved. But we're not saying that this should be 0.8. Okay, that's not correct. All right, because there are 3 possible crimes. So what we're trying to say is, of the 3 crimes, what's the probability that one of them, this is 80% of all property crimes. All right, so what we have to do with this is we have to use that binomial formula 4 times to be able to figure out the probabilities. All right, so remember our formula. P of x is equal to n combination x, p to the x, q to the n minus x. And we're going to use that 4 times. We're going to use 0, 1, 2, and 3. And we know in this problem that n is 3, at most, because there's 3 possible crimes. The probability of success is 0.80 or 0.8, and the probability of failure is 0.2. So let's just go right through the list, and we're going to find p of 0, p of 1, p of 2, and p of 3. And we can just set them all up at the same time. All right. So we know p of 0 is going to be 3 combination 0, 0.8 to the 0, 0.2 to the 3 minus 0. All right. And we're just going to do these all. And you can see that, okay, well, that's going to be 0.8 to the first, and 0.2 to the 3 minus 1. Right, so these aren't too difficult to type in. It's just going to be a little bit painful to do it, but no big deal. So that's going to be 0.8 squared. And by the way, this is a 0.8 as well. And then times 0.2 to the 3 minus 2. And then finally 0.8 cubed, 0.2 to the 3 minus 3. All right, so we're going to shove all this in our calculator, not at once, because that would be painful. But let's just set up the first parenthesis, 3 math combination 0. And we're going to multiply that by 0.8 to the 0. And then we're going to multiply that by 0.2 to the 3rd power. All right, and this should actually work out to be pretty nice, like 0.008 or something like that. So 0.008 exactly. All right, so that's not too bad for us. All right, now we'll use that trick, second enter, and we're just going to change all of these to 1s. All right, and by the way, the numbers should be relatively tame because we only have 3 selections. If we had a lot more, then the numbers wouldn't be as tame. Right? So this one's going to be 0.096. So let's just write those in here. So that's going to be 0.006 and then 0.09. I think it was 0.96, right? And then do it again. So we're getting close. So it's going to be a 1, and this is going to be a 2. And then this last one is going to be another 2. And that's going to be 0.384. And then the last one should be somewhere around 50%, because the other ones, if we add this up, that's about 10, and this is about 38, so it should be like 51%. But let's just go ahead and compute it, just because we don't want to trust a mathematician's guess. And I'll show you a trick to make sure you've done these right at the end, although I'm assuming most of you guys probably figured out the trick to make sure you got your discrete distributions correct. But if not, I'll show you. All right, 0.512. All right, so we have 348 and 512. So 384 and 512. And we're just going to go ahead and copy these into the probabilities. And our probability is P of X. So that's 0.006 and 0.096. And then 0.384. And then finally 0.512. And now here's how you check. If this is all the possible outcomes that could occur, then the sum of this probability distribution, the probability should be 1. So does this equal to 1? That's the question. So of course we don't want to trust my intuition as to whether it adds up to 1. Let's use the calculator. All right, so we're going to go in our calculator and we're going to say 0.006 plus 0.096 plus 0.384 and plus 0.512. And unfortunately, if this doesn't add up to 1, then we have to stop the video and do it over again. It adds up to 0.998. All right, so that's pretty close. Might be rounding error. Let me go back up just to make sure I didn't make any typos or copy errors or anything like that. I did. This is 0.008, not 0.006. All right, so that's a good way for us to check. So I'm going to go back here. And some of you were probably screaming at me earlier, about 3 minutes ago. So this is 0.008. This changes to 0.008. And I bet you, if we go through and just change this, let's clear that. Hopefully we can second enter. No, it doesn't matter. So 0.008 plus 0.096 plus 0.384 plus 0.512. And that gives us exactly 1. All right. Now, again, I picked really small numbers, so I knew it would work. All right. So yes, we've done this correctly. So that's how we construct our probability distribution. Now that's the hard part of this problem. All right. Now we have to go through and use our old formula. So let's use the old formula to compute the expected value in the standard deviation. Okay. So for letter B, now remember, expected value using the old formulas. Mu is equal to the sum of x times p of x, and then sigma is equal to the square root of the sum of x squared p of x minus mu squared. All right, so that's the old way. So let's do that the old way. So remember we had x was 0, 1, 2, 3. And our p of x that we just got, hopefully I don't copy it down error again. So 0.008, 0.096, 0.382, 384 again, and 512. Okay, and we're going to do x times p of x. Right, this is going to help us to get our mean. So we know that 0 times anything is 0, 1 times 0.096 is 0.096. Twice 0.384 is going to end up being 766. All right, but again, let's just go back and check. So 2 times 0.384 is 768. Excuse me, I think I put 766. I did. Just write that on the teacher evaluation. Can't multiply 4 times 2 correctly. All right, and then the last one, this is going to be 1.024, I believe. All right, but let's just, no, not 1.024, excuse me. It's going to be 1.536, I believe. All right, but let's multiply it anyway. I'm multiplying it by 2. So 3 times 0.512, 1.536, 1.536. Okay. And then we're going to add these up. All right, so let's just go to our calculator. 0.096 plus 0.768 plus 1.536, and we end up with 2.4. So our mean, and we didn't, I didn't ask you to interpret it, but the mean is 2.4 this problem, right? That means we would expect about 2 or 3, all right, because it's right in the middle. So that means we know about 2 or 3 of the 3 property crimes would be solved. That's what we expect, okay? Now let's find the standard deviation. So I'm going to clear this out. Let's hold on to 2.4 because we do need that. All right, so I'm just going to write it up here that mu is 2.4. So let's hold on to that. Let's get another column. In fact, we could just do x squared, which is 0.149. And we're just going to multiply these two columns to get x squared p of x. Now we know that 0 times anything is 0. 1 times 0.96. So we still have 0.96. Now we're going to take 4 times 3.84. And we're going to take 9 times 0.512. All right, so we get a 1536 or 1.536. And for the other one, hold on a sec, that's 4 times 0.384. So that's 1.536 and then 4.608. And the last thing we're going to do is add these up. So we go in our calculator, 0.096 plus 1.536 plus 4.608. All right, so that gives us 6.24. That's a nice number. All right, and the last thing we're going to do to find the standard deviation is we're just going to use this formula. So sigma, which is going to be equal to 6.24 minus 2.4 squared. Okay, so we did this in section 10. It's the old news to us. So let's throw in the calculator and be done with this part of the problem mercifully. Second square root, and that was 6.24 minus 2.4 squared. It'd be really nice if it was one of those really nice numbers, but I doubt it. 0.6928. All right, so let's just say 0.69282, just because we can. $9,282. All right. So that was the old way of doing things. It works. All right. Now, for part C, let's find the mean and the standard deviation using the binomial formulas. And you might remember that the binomial formulas are a little bit easier to work with. And when I say a little bit, I'm being facetious because they're a lot easier. Remember, mu is equal to n times p. Remember that n was 3 and p was 0.8. 3 times 0.8 should be 2.4. All right, but just in case you don't trust me, with good reason. So 3 times 0.8, which is indeed 2.4. All right, and then remember our other formula for sigma, the square root of n times p times q, which is the square root of 3 times 0.08, I'm sorry, not 0.08, times 0.8 times 0.2, which was q. And we got q all the way back at the beginning. All right, so remember we found q all the way back here was 0.2. All right, so it's not like some number I'm making up. Let's throw that in the calculator. And we're going to say square root of 3 times 0.8 times 0.2. And that gives us 0.69282. And then some runoff, 0.323. Boy, if only we had seen that number somewhere before. Hint, 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 we have, but that's okay. So 0.69282. All right, so let's comment on the parts B and C. So let's go back up to part B. And, oh, hey, we got 2.4 for mu. And we got 2.4 for mu. Okay, so if you're a logical person like me, this is very, very difficult to do to get 2.4, part B. Part C, we got 2.4 with very little work. In fact, we didn't even have to do the combinations or anything like that to get there. All right, so mu is the same for parts B and C, but part C was much easier. All right, so what about part for sigma? Well, so we get 2.692 right here. And up here, oh, we got 2.6928. All right, so I'm sorry, we got 0.69282, and we got 0.69282 down here. These numbers are the same. In fact, if we go into our calculator, check this out. This was the value that we got by utilizing the standard deviation for the discrete distribution. Remember, we got 0.69282, and then we have 0.323, and then we have 0.323. These two numbers are the same, accurate to 2, 4, 6, 8, 9 decimal places. The likelihood that those two are the same by coincidence is extremely low. All right, there has to be something going on here, and there is. All right, so very similar to what we just responded for mu, we can say that sigma is the same for parts B and C. All right, but again, part C was much easier. I underlined it 4 times or 5 times or 6 times, whatever it was. All right. And now I hope what you're seeing is the power of the binomial distribution. All right. So that way we don't have to go through and we don't have to create these probability distributions. We could if we wanted to. All right. But most of us don't want to. Most of us just want to use the n times p or the square root of n times p times q. So hopefully you see that there is a relationship between the two. For anybody that's interested in higher level mathematics, you can see what happens as the number of samples approaches infinity. And that's where you would need a little bit of calculus to be able to work with those. All right, but pretty cool that these work out pretty nicely. All right, so that's the last of our binomial distribution. The last distribution we have to look at is the discrete distribution called the Poisson distribution. So we'll look at that in the next video.